So our first speaker, Kelvin Wang. Dr. Wang is the professor of civil engineering at Oklahoma State University and holds the Gilbert Cooper and W. Steele Chair. His research interests include pavement engineering and technologies of 3D laser imaging sensors and software solutions of the highest performance. His career started at Arizona DOT in '89, and he has been a university faculty member since '93. The ASCE 2011 Frank Masters Transportation Engineering Award was given to Kelvin for his innovative research on automated pavement survey and data analysis technologies. He is an associate director for Region 6 University Transportation Center and the Southern Plains Transportation Center. So let's welcome Kelvin up to the stage. And one note, I'll leave it up to the speakers if they want to field questions during their presentation or after. We got about 35 minutes per speaker, so you guys can kind of decide how much time you want to leave for questions.
Thank you, Darren. Kind of it's a little bit shocking to have a room that can hold like 500 people. I think we got a good audience here.
We have quality.
Yes, exactly, Judy. Thank you. Thank you, Darren, for the introduction. I thought I only had 20 minutes, and 35 is great. It's flexible. If you have questions, you can jump in during my presentation, or I can take questions afterwards. It's great to be in Nashville again. I was here like in the 90s for a conference and then never came back, but it's a great city and it grew quite a bit in the last 20-some years. I actually represent two organizations. Of course, my full-time job is a professor at the university. We also have a business called Waylink Systems, which is based actually at the university. But it has its own mission and liability and everything. So we've been doing technology supplying operation to the payment industry for more than 15 years. Even though we are not very big, but I think we have pretty good technology in some area in payment data. So I'm going to talk about two parts. The first part is what we have today, what we're doing right now, what we are able to do in the field. The second is new developments and challenges, and what we are trying to incorporate in terms of inertial profiling into the 3D system, and also the deep learning effort we started early this year. The current 3D system, some of you may be familiar with our work, others may be not. We have been doing payment data collection since the 90s in the technology development area. We came out in Arkansas in the mid-90s and late 90s. We actually had some system running. And the current system we are introducing right now actually is already 2 or 3 years old. It's probably the 5th or the 6th generation. If you have seen our prior generations, they looked very, very different. And this particular van we had for about 3 years now, it's a very compact design, but it's multifunctional. We are able to do 3D payment surface data collection and several other data types that we're going to introduce to the audience today. This particular system has been used in South Africa, in Brazil, and in China, and of course in the US. We have FAA Tech Center in Atlantic City, and also Indiana DOT, among other users. So they are using our 3D technology. We term the technology called PaveVision 3D, and we can do 30,000 3D lines per second at 60 miles an hour, and that's is still the record, and we remain the leader in this area regarding providing the highest quality 3D data. So this was a shot actually came out of that came out of the Smart Road in Virginia a few years ago. I think it was an RPARC meeting or Payment Evaluation Conference. I'm showing several visuals. I hope the displays are good enough for you guys at least to understand what the quality we are able to get. This is a 3D surface, and those data sets I'm going to show you, they were collected about 4 years ago. So you can tell that the technology is leading regarding the quality of data. And I can say that even today, regarding the definition and the quality of the data, we are unmatched what we can do. For example, this data set was collected at 60 miles an hour, 100 kilometers per hour at Interstate 35, north of Oklahoma City. And this is a comprehensive data set. As you can see, we have the intensity data, we have the range data, that's the big swing of the 3D, we have a right-of-way, we have profiling, etc. A close-up of this particular data set, as you can see, this is the same data set collected at 60 miles an hour. And this is a full lane width, roughly 13.5 feet wide. And this is the zoom in of this particular deterioration or the corner of the concrete slab. And you almost can see that something was done to somewhere. There's a circular pattern that actually was a drill. And that particular drill actually caused the deterioration of the corner. And subsequently, they actually filled it with asphalt materials later at two different stages. The first stage, of course, is to fill the drill itself, and then later on, they filled it again. So this is another close-up. So this is captured at the 60 miles an hour. And we were very kind of proud and shocked when we saw this data at 60 miles an hour when we came back from the field trip. So that's more like a demo image I show to people all the time. And we also have our own automated processing software called Automated Distress Analyzer, ADA. And this is what the software we're using, trying to classify and identify street cracking in this particular case. As you can see, there's a curb, concrete curb, and then the pavement itself is asphalt. Okay, so this is, so essentially we have a world-leading definition and resolution 3D data collection technology. We also have been doing airport runway surveys for a number of years. I'm going to give you an example. This is a representation or diagram of a runway on Husfield in Atlanta. Each slab we run twice with the vehicle. Okay, they have 8 slabs, so we run 16 times. And then the top of this figure is the raw data of the multiple passes of the data. And the bottom is the stitched multiple passes data to form a virtual runway. And from this new stitched data sets of a virtual runway with geometry accuracy, and we're able to use PCI analysis to determine the distresses from there. And this process has been around for over 10 years, and we're working with FAA, the Tech Center in Atlantic City, on further improvements of the system. And for instance, this is one of the deliveries we have to give to FAA through a research project that we'll be able to establish the 3D surface of a runway, and we can do PCI analysis from there. Another example of our airfield work is groove evaluation. For those of us who have done work on airfield or know something about airport payment system, all the airports in the US have grooves, okay? We know that FAA has a documentation set called Advisory Circular, which is very similar to AASHTO guidelines or AASHTO standards. The big catch on the advisory circular is all the airports have to follow the AC advisory circular in their design and management of the airports. And they do have a circular called AC 150 slash 5320-12C. And this particular AC circular determines the groove evaluation methodology and essentially the groove depth, width, and spacing. So now a common question or conception is we develop grooves on the airfield pavements to improve friction or tire pavement interaction. That's true by a large degree, but the number one objective of the grooves on runways is not to directly address friction, is to address the issue of hydroplaning so that water runoff can occur as rapidly as possible. The bottom line is runways cannot have water on the surface. So that's the primary objective of grooves. So the grooving performance is becoming a very critical part of the pavement management system for runways. Now the dilemma was even though FAA has an advisory circular to define the depth, width, and spacing of grooves, and that AC has been run for probably more than a couple of decades. There has never been a technology to evaluate the performance of grooves after the runway has been put into operation. Okay, at the beginning, new construction, yes, you can measure it, use ruler and whatever, but whenever the airport is in operation, for those 5, 10, or 20 years, it's very difficult to measure the performance of the grooves if they are still okay. The grooves have the rubber accumulation, which is a very big issue. Essentially, the rubber of the tire actually got caught up in the grooves and then they fill up. And the other thing is the surface deterioration because of the wear caused by the tire at very high PSI and speed. So traditionally, people were using, if they want to do it, using the line of sight point lasers to do the groove analysis. In our new technology, we can cover the runway in its entirety with 3D. So we developed a filtering algorithm and software trying to essentially identify grooves and its dimensions automatically on the entire surface of the runway. So this is the filtering algorithm we developed. And as you can see, the top one is the raw data, the bottom one is the initial filtering, and we use geometry contour algorithms, and then we're trying to do backward and forward traversal, trying to determine where the grooves are, and then of course the depth and the spacing, and also width of the grooves. And in addition, since we are able to capture the pavement surface in 3D, we actually can calculate groove volume, and that has never done before. We think it's an important parameter because the primary objective of grooves on the runway is to maximize water runoff rate. And then, of course, the groove volume would play a critical role in that process. And then we actually, for those of you who visited the Tech Center of FAA in Atlantic City, they have, the pavement group has an indoor runway, which is roughly a quarter of the length, but about half of the width of a full runway, and then doing all sorts of testing through construction cycles. And they are doing construction cycle 7, and we'll do construction cycle 8 pretty soon. And we actually went there to do all kinds of data collection and algorithm validation. And this is part of the data we actually collected. As you can see that the grooves are captured and in the transverse direction, And we have a pretty high successful rate, actually very, very high successful rate, and 90 plus, sometimes 99 plus percentage, all groups are identified correctly. And this is an example of the groove evaluation we conducted on the construction cycle at the FAA's indoor test track. So I conclude the first part of the presentation on our current work. The other thing I did not add here is that we are also doing tunnel and rail inspection with our technology in China, and we already mounted our customized tunnel measurement system, and we are actually developing our high-speed rail system, highly customized with 7 sensors at 0.1 millimeter resolution to 0.5 millimeter resolution across the entire rail track. So that's something new that we are doing, and we hope to have some results in papers and in journals soon. A little bit unfortunate because the US really does not have a whole lot of tunnels, and we have limited rail operation at very high standards. So the northwest corner we have a cellar, but other places heavy haul is big, but traditional rail line is not of high standards. Anyhow, without further ado, I'm coming to the part 2 of new developments we have. The first one I would like to talk about with the actual data. This first time, we've been doing this for a couple years, but this is the first time we've been showing the data. We call it WIS initial module, okay, for longitudinal profiling. We are very happy that we achieved a milestone with our 3D sensors and integrated inertial module. As you can see from this slide, this particular black box called WIS is a fist size sensor we designed and produced ourselves with components, of course, from the semiconductor industry. So we have our own hardware filtering and the power system. The class 1 or higher inertial sensors require very stable power supply, and we use essentially a military-grade power supply and also frequency filtering chips inside this module. And we put this module into our sensor, into our 3D sensor, so users actually wouldn't be able to see the existence of this particular hardware at all from the outset, okay? So this particular sensor, actually, I'm going to go back to tell you where it is quickly. For example, on this particular, I think I can use my mouse. Can you guys see the mouse? They actually will be mounted inside this 3D module, okay? And so that's the extent of hardware, and everything else will be integrated, and a user actually would not be able to see this particular module directly. We, of course, use the South Dakota road profiler principle. Many of the vendors today rely on that principle, which is a very robust approach. I believe the person who invented this device is still working today. He's the head of the South Dakota DOT's research program, David, if you know him. I don't think he's here today. But that was a fabulous design at that time, and we all refer it as South Dakota profiler as the term to referring to this particular invention. What we did is we did 3 tests. Each test we run more than 10 passes, okay? The test section number 1 is about 1,100 feet, and we run it at 30 miles per hour, okay? And then the next section is about the same length. We run it at 40 miles an hour. And the third one is 1,700 feet. We run it at 60 miles an hour. Now, those test sections, they are not controlled sites. So we are very limited regarding how we can maneuver. And it all depended on the driver who really had to control the vehicle. So every pass we do, we'd better run the same location. So the data you're going to see, even though we had no control of the test section regarding traffic, those are live streets or highways that have other vehicles running around, but we were able to achieve what we can show you today. This first test section was 30 miles an hour. We run 12 passes, okay, same day. The repeatability of 3D data, this is equivalent to the traditional cellcom height data, okay? So, but the height data information in this particular case came from our 3D sensors. So those are the raw 12 passes. We did not discard any path data, okay? We just did 12 passes. We did the statistics with ProVal, and we came up with 94 on the left side and also 94 on the right side for repeatability of 3D height, okay? This is a very critical parameter in the TTI certification process. Now, by removing the worst 2 and keep the best 10 passes, the data, we improved 1%, okay, which is good. And that's exactly what TTI certification does. They allow you to collect well over 10 passes of data, and then you keep the 10 best for the certification. We're able to achieve 95%. Now, this would be the profile data we get from the test section 1. We are achieving 97% and 95%, even higher than our 3D data. That tells you that our sensor data from the accelerometer module, WIS, has a higher quality based on this test, okay, than the 3D sensors, which is good news because we designed that particular module at extraordinary precision and bias levels. All right, so I'm going to run it a bit faster. Darren just told me that I got probably 9 minutes left. This is still on test site 1, repeatability of profile data from the left and also right side, okay? 97, 95, and repeatability data from the left side. Now, this is Ames. Ames is, we use the TTI certified device. We actually physically certified our device from Ames. We purchased Ames device 4 or 5 years ago, and the Ames achieved 92% repeatability of the profile data. And for the Ames from the left side is 92%, and as well. Now, the continuous IRI data is the key because users like you guys, you worry less about the other data sets. The certification process is concerned about them, but not the actual usage. As you can see that, Ames is yellow and our WIS system is blue. We shifted a little bit so you can compare the data results for this particular 12 passes, and we do real well. We match almost exactly of the certified Ames device, okay? So I'm not going to read all the numbers. Test number 2 is 40 miles an hour, about the same length. Repeatability is high, about 94% on both sides. And if we take the 10 best passes, we achieve 95 and 96, actually 96 and 97 repeatability, so which is very, very high. And repeatability of profile data is over 90%. If we do the 10 best, we do over 95%. And the Ames data is 97. Okay, so we are matching the Ames data real well on the repeatability of the profile data. And this is Ames 97, which is very good. Okay, and the IR data sets, again, we shifted a little bit to show the comparison, and they match almost exactly as well. The Ames data and our own WIS data. All right, 60 miles an hour, The repeatability of the trial passes is a little bit worse than the past, right below 90, okay? It's very high speed, driving-wise. And if we have the 10 best passes, we are approaching 90. And this is repeatability of the profile data. All trial passes, we exceed 90 on one side, below 90 on the other side. And if we use the 10 best, we are all above 90%. And we have the Ames is 95. So in this particular case, at high speed, the Ames is slightly better. And then the II results match real well. So we are pretty confident that our system is able to pass certification, and we have some more work to do to get this used by users in the field, and we are planning to do that pretty soon with our several current users. The last thing I'm going to talk about is called deep learning, and we all know that finding cracking is not easy, okay? I was very naive in my early years doing this development. I thought in the late 90s, give me 5 years, I'll get it done. 20 years later, we're still making gradual progresses, not really solving the problem right this moment. If somebody tells you that they got cracking 90% or 95%, I agree that they probably worked on some sample images, but you cannot achieve that level at network level at all, fully automated, okay? So what we are trying to do is to do detection and classification of cracking with full automation. Okay, we cannot do that with traditional image processing approaches. Okay, it's very, very difficult. I'm not going to read the text to you. Here's some examples. Those are bad examples I'm giving to you. That what our software did with certain images. For instance, we have. We got a lot of noises identified as cracks in this particular case. In this particular case, if you can see the details, we caught a lot of cracks, but not all of them, okay? So, and in another case is grooved payments. We have, we caught all the cracks, but we got one groove that's classified as a crack, okay? So it's a problem there. And this kind of errors occur very, very frequently, and manual editing is very, very expensive today. All the technology integrators or suppliers, they have these issues, okay? It's not just our issue, it's industry-wide. So why we want to do deep learning? I played with neural networks in the 90s as a young researcher, and I did not make a whole lot of progress other than playing with some simple algorithms. They work well, but mostly they did not work for our applications. Early this year, you guys heard of Google used a machine called AlphaGo to beat a human in chess playing, and it's amazing what they did. And I don't want to go too deep into that. I can spend 3 or 4 minutes just talking about that. It's just amazing. When I found out, I asked my postdoc, I said, Alan, can you figure out what's going on here with this deep learning, the neural nets? And he came back, he essentially told me, he said, Dr. Wang, 10 years ago, exact 10 years ago, in 2006, there was a revolutionary paper published by a professor from University of Toronto that changed the entire landscape of artificial intelligence. So in the last 10 years, they literally lots of work done, particularly industry, like people like Google, and now Facebook and Uber. And those people, they essentially, each organization has a couple hundred people. They do nothing but do artificial intelligence for deep learning. Deep learning is nothing but very high number of neurons and layers interconnected like a human being, okay? And they're trying to teach that system to learn and to do things for us. So I'm not going to do too much in the other introductions, but the chess playing is just an example of the success of deep learning, but the most prevalent applications today are all on images, okay? For example, in this particular example, it came from a study recently, how to tell that this photo is a person, okay? It's very simple. A 3-year-old child or 2-year-old child can know that. But for a machine to do that at 100% accuracy among millions and millions of images is not easy. It was not easy. People solve the problem today. They can actually figure out it's a person, and they actually go to deeper who that person is, okay? And an example is in China, there's a Walmart in Shenzhen. They lose merchandise all the time, okay? They installed a deep learning imaging system. They caught all the thieves in 1 week, all of them, because they came back every week. And people cannot identify them, but they could use this deep learning technology. They caught all the shoplifters in 1 week. So that's how the applications can be used in the field. So for us to do this on pavements, it's not easy. Currently I have a team about 4 full-time staff, about 6, 7 PhD students. Their primary work since this spring is on this thing. So this is our current structure, how to break down an image, how to use simple algorithms, but connect literally tens or millions of neurons together and process those images, okay? So I do not have actual results today. We are making progress. We are hoping to get a paper out before the holiday break. And then hopefully next year sometime we'll be able to implement a deep learning system to process for cracking first and then for other types of distresses later. So you ask me, how long it's going to take you to do that? I'm hoping that it's a gradual process. Maybe in 2017 we have some applications, and every year we would have some updates and to do this. So I'm really close to the time. So I'm going to go to my last few slides. And it's a very difficult task, okay? So it's not easy. But first we build image libraries. We have 10,000 image libraries today. What are those image libraries? Essentially the raw image and then the process image. The process image is all double-checked by humans. The processed by humans, they double-checked for accuracy. That's a typical example of, we have to feed those sample images, literally in thousands of them, both flexible and concrete, into the learning system, okay? It is a very, very challenging task, but we look forward to provide some further update later this year and also every year from now on. And we thank all the funding support from different agencies, and I can take some questions. Yes?
So when I keep looking at using the 3D sensors with the accelerometer, it seems like it would allow you to pick which longitudinal profiles to use. And one of the most interesting findings, I think, for us users would be what's the variability of picking different of those longitudinal profiles.
Right, that's a very good question. Yes, yes. We actually we had this concern at the very beginning. The data you see right now is our first stage to prove that it can work, and we know that it can work. The data point we are picking is right underneath the sensor. That's the most highest quality 3D data we can get. Again, we can spread out. Essentially, we can establish the entire profile, real profile longitudinally for the pavement. If there's a need to do that, it's relatively straightforward. But we are using the data right beneath the sensor for that purpose today.
I think we're kind of out of time. If you have any more questions, let's catch Kelvin after the presentations or grab him for lunch. So thanks, Kelvin. Pretty amazing technology.
Okay, thank you guys.